Confirm that you can see my screen.
Yes, sir.
Yes, sir. You can see the screen, sir.
I can see your screen.
Confirm that you can see my screen.
I can see your screen, sir.
Yes, I can see your screen.
Okay, we're looking at application of embedded system in robotics, part 3. When you get the lecture material, you can, or rather when it's uploaded on YouTube, you can uh, take a little time and look at my profile. So let's just move on. So far, do I drop this? So far, we have looked at sensors. Last yesterday, the students from POT made presentation on sensors. I think we take presentation for presentation from people in mechatronics, students from mechatronics and medical engineering. So the workflow for today's lecture will be sensors, signal conditioning, microcontrollers, actuators, and the loads. Specifically today we'll be concentrating on microcontrollers. This is a typical prosthetic arm we have discussed. Of course, embedded in it, you have sensors. When I look at the price, $1,380 US dollars. Keep on telling us that anybody that is healthy, all parts of your body are functional and are working. That person should be grateful to God. This is what an arm can, not even a full arm, just part of it can cost. And it's just initial cost. The maintenance cost is not there. So let's proceed. Today we're looking at overview of microcontrollers used in implementation of robots. And so there are many of them. We just have to consider few. You have Arduino Uno, you have ESP32. Within the Arduino family, there are many of them. Um, Within ESP32, there are many of them. Let me just show you some things. Um, just a moment. family, I will just project my screen again. Within Arduino family alone, there are many things there. So within Arduino family alone, we have, look at this. Somebody just read out what you see. Let me confirm that you can see my screen. Start from up.
Sir, close your cursor. Remove your cursor so that we can see.
I can hear you.
You mean where your cursor is going around?
Lead microcontrollers or the stuff that one can do with Arduino.
We have Arduino Uno Mini, Arduino Demiranov or
Decimal.
Decimila, Arduino Nano, Arduino Mega 2560, Arduino Mega ADK, Arduino Leonardo ETH, Arduino Micro, Arduino Explorer, Arduino Mini, Arduino Ethernet, Arduino Fio, Arduino BT, LilyPad Arduino USB, LilyPad Arduino Pro or Pro Mini, Arduino NG or older, Arduino Robot Control, Arduino Robot Motor, Arduino Gemma, Adafruit Circuit
Okay,
Playground,
it's
Arduino
okay.
Yonmin.
It's okay. Thank you so much. The essence of asking you to look at it is to let you know that there are many things available. Remember, one of the reasons for Trust course is to expose you to existing technologies that are available that can help you to realize your project. For example, if we check Arduino Mega, if we check Arduino Mega, you can see this is Arduino Mega. Different from Arduino Uno, but they belong to the same family. They belong to the same family. Of course, you can see that the price is different. So these are the stuff we get to know. We need to keep abreast with technology. Let's go back. You check ESP. So another person, if there is a woman in the meeting, read what is here. Try to read from what is from on top. Is there no female in the
Sir,
meeting?
let me read. The first one I say E. Okay. I'm not seeing your this thing again. Your question. Okay.
Okay, go ahead and read.
Okay, the first one is ESP32C5 Devo model. The second one is ESP32P4 Devo model. The third one is ESP32H2 Devo model. ESP32C6 double model, ESP32S3 double model, ESP32C3 double model, ESP32S2 double model,
It's okay.
ESP32.
It's okay. Thank you
Okay.
so much. So these are the microcontrollers one can actually explore. For example, this belongs to ESP32C3. You can see it's very small. It's very small. It's very small, can be used to implement miniature projects. This one is a bit bigger. All of them have different features. So you get to know the features they have and how to explore them depending on the project you are doing. So these systems, these microcontrollers can be simulated. They can be simulated. I'm talking from the practical point of view. They can be simulated. You can actually design a project with them, simulate it before your construction. We're just going to do a practical something this night. So we start with Arduino Uno. We've discussed about sensors. So let's just try to read a sensor and display it possibly on a virtual terminal. So we go over here. Let's start with Arduino. This is Pro Tools Professional. The essence of this course is not to teach you how to use Pro Tools Professional. It's just to expose you to what is existing so that at least you know what you can use to realize your project and then devote time to study them further. I pick Arduino Uno. So we pick either this or this. Any of them should work. So that's that. Is there any, let me see if there is any sensor that is available. You have to be specific. Which sensor do you know? Okay, let's take for example, let's take just temperature sensor, let's say thermistor. Okay, which of the thermistor? We just pick. Okay, we can pick this then, and then we can also pick. Let me pick LM35 as well. It's a linear temperature sensor, LM35. So we drop them. We'll just drop Arduino. I need to, before we begin to do our connection, let's look at Arduino Uno properly. So I made mention the other day that if you want to use any component, you have to check the data sheet. Now, Arduino Uno is before us. You can see Arduino Uno has how many A's here? You get to talk. If I don't hear your voice, that means it's either you're not hearing me or the network is not true.
It has 6 A's.
How many A's do we have here? A0, yes, another person, A1.
6.
A2.
A2, another person. Please unmute yourself and talk. This is supposed to be an interactive class.
So we have 6 A's.
6 A's. So A0 to A5.
Yeah.
Do you know what those A's stand for? Do you know what they stand for?
Yeah, I think the A stands for analog pins.
Okay, that's correct. Those A's there stand for analog inputs.
Analog input.
You said?
Okay. No, I'm trying to get you, sir. You said it's analog input.
Yes, analog inputs. Those A's stand for analog inputs. You know, for you to really get signal from the physical world to the digital world, it has to go through analog to digital converter. You have your sensor here, you have signal conditioning. This represents your analog to digital converter, which will convert the signal to digital equivalent of analog signal. Microcontroller is a digital component. It's a digital device. It can only accept information in digital form. So, back to what we are saying, this analog channel makes us to know inside this microcontroller Atmega 328P, there is embedded inbuilt analog to digital converter, and there are 6 of them. How many?
6.
6 of them.
6 of them. Please pay attention to details. Some of you that are familiar with me at level of your undergraduate will have known by now that most times I don't set questions outside what is discussed in the class. It's one of the principles I have adopted in life. There is no point trying to test people on what is not discussed. If I will test you outside what is not discussed, I will tell you to read about it. Because there are several things one can study in this life, and you don't expect people to study everything and know everything. Nobody knows everything. Purpose of exam is to test you whether you understand the concept of what is discussed. So as we do this thing, you pay attention. By God's grace, I may upload the lecture on YouTube tomorrow, and you go there and listen to it properly again if you want. So we have analog channels, and what it means that we can connect up to how many sensors to this I don't know how many sensors?
6 sensors.
These sensors, these different sensors at the same time. So we move away from the analog input, we go to the output. We have D0 to D13. These are digital pins, which can function as either input pins or output pins, depending on how you configure them. You can actually use them to drive a load, drive a robot, drive an actuator. You can also use them to accept digital inputs. There is also what is called pulse width modulation, but we don't want to discuss that now. This is not purely mechatronics. Pulse width modulation is a technique you use in controlling DC motor and some other things. But you can see we have D0 to D13, and then you also have room for serial transmission, serial communication. You have RSD and TSD. Can transmit with this one. I think we're going to use this one this evening. And you can also receive with this one. So, having looked at the architecture of Arduino Uno, I expect you to look at this architecture very well. You are supposed to be able to describe the architecture of Arduino Uno at least. Describe it, describe the external pins. I don't expect you to get into details, inside details, because that will take you a long time. And within the time we have, I don't think that is something one can do. Okay, so we move on. That's Arduino Uno. Now, let's remove this. What is this? Okay. We pick one again. And we pick a sensor this time around. LM35 is a temperature sensor. LM35. Where is this line coming from? It's like somebody, but I didn't share the whiteboard. Where is this line coming from? LM35 is a temperature sensor. So look at it here. That is physically, this is what you see in markets. But then in simulation, we have this. I don't know where this line is coming from. So we wire this together. We just have to wire this. So we connect before we finally hook it up. We pick 5 volts power, which is usually called VCC, 5-volt power supply, power. I just want to be sure that the polarity is correct. If this is power, and then we pick ground, and then we check the output. Somebody should tell me, what can we use to check the output? we can actually use a voltmeter. We can actually use a voltmeter, DC voltmeter, to check the output. Okay, we run the simulation. Let's see. It's throwing an error saying that something is not defined. Okay, so let's remove this one first. Confirm what you can see on screen.
Yes, sir, we can see it, sir.
What?
Voltage of 0.27 volt as output, and
Okay,
a temperature of 27.0 as input.
okay. So you saw very well. Part of this course, I know that some of you in biomedical engineering, your course has something to do with instrumentation. Is that correct?
Correct, sir.
Good. Please pay attention. It may not concern those people from POT, but for sure, people from mechatronics and biomedical instrumentation concerns you. Even POT concerns you. It's just that I don't know whether they'll be able to absorb it. So we pick, I open Excel sheet. We open Excel sheet, and one of the things I want you to get from me or learn from me, you have to be very good at what you are doing. Be very good at what you are doing. If you want to become a lecturer, you really have to spend time and develop practically. Okay?
Just one, and that's what
So that
we
when
use.
you are communicating with students, you have to impart knowledge, not just theoretical stuff. We want to do a bit of instrumentation now by taking readings. So we call this one temperature. Temperature. We call this one, let's call it output. Output. So this is temperature reading. This line, I don't know where it's coming from. I just hope that it's not a screen problem. Output voltage. So we take reading 0, 1, 2, 3, 4, 5, 6, 7. Sorry, 6, 7, 8, 9, 10, 11. Just see is that we're in laboratory now. 12, 13, 14. So let's stop here where you can see my screen. Let's just stop at this level where you can see my screen properly. And then possibly we move this to this point and move this to this point. We can move this to this point. So, and we can centralize this reading. Okay. Also centralize this. So let's work with reading 0 to this. We go back to our lab and we come here. So we move to temperature of, let's go to temperature of 0. So when the temperature is 0, what is the output voltage here?
0.
0.0.
Also zero.
So with 0.00, when it is 1, what is it?
0.01.
Eh?
0.01.
0.01. Okay. So 2,
0.02.
3,
0.03.
0.03.
4,
Continuously, NASA.
5,
0.05.
0.05.
0.05. So we can already see a pattern that this this temperature LM35 is linear. So we can see a pattern there. So 0.02. What is the multiplication factor now? If we divide 1, I mean, what do we multiply 1 with to get 0.01?
Times 10 to power minus 2, sir.
10
You
to,
divide by 100.
okay, times 10 to power minus 2. That is 0.01 is equal to actually that. So 10, and this is if we convert 0.01 to millivolts, what is it? That is 10 millivolts. Am I correct?
Yes, sir.
Am I correct?
Yes, sir.
I mean, this is 10
Please
millivolts.
come again, sir. Please come again, sir.
If
Yes, sir.
we,
It's 10 millivolts.
this is in volts. This is in volts. This is in volts. So if we want it to be in millivolts, I mean, if this one is, if we create another table and is in millivolts, then here is 0, here is 10, here is 20. Look at it. Are we together?
Yes, sir.
The people from POT. Are we lost?
Yes, sir, we are not.
Eh?
Yes, sir.
But this is simple mathematics. This simple mathematics. It's not really anything difficult. Milli means 10 raised to the power minus 3. Okay?
Yes.
Kilo means 10 raised to the power 3. So millivolts means 20 times 10 raised to the power minus 3, which will give you back to this. So we can actually multiply this and use formula in Excel. If this is a product, and then we can say that this is of course this is C2. This is C2, okay, to C3, no, and then we can multiply it with what to get the subsequent value, whatever it is. Hold on.
It should be C4.
This is C what? This is C3 now. Or rather, this, whatever value is here, what we are saying that this is B2 multiplied by, it should be in capital letter, B2 multiplied by what do you call it? 0.
10 to the power minus 2.
0.01. That is 10 millivolts. Does it make any sense? Does it make any sense? Well, we are talking about products. We want to, cancel. We want to get what is here. In any case, this is increasing by 0.01. So product of what we say product C2, C3, we say C, it should actually be, this is, let's watch where we are. This is C4 now.
That's B4. That's
B4, right?
Yes, sir.
That's B4. Then we multiply B4 by 0.01.
Yes, sir.
So that's it. And then we just drag it. We are giving it an equation. We just drag it. Is that correct?
Yes, sir.
Yes, sir. Yes, sir.
So the same thing applies here. This one is
Increasing by 10.
somebody tell us what should be here. Talk now. This is C.
Product of
Product of C3 for example, here, not C4. C4
Product of
multiplied by what? Multiplied by 1,000.
10.
That's 20. And then
Okay.
we drag it. Are we together?
Yes, sir.
Yes,
Yes, sir.
sir.
We're doing instrumentation now because we want to instrument this sensor so that we can program it. Some of these things are not they are not rocket sciences. These are the things one can actually do in a lab. So having gotten the readings, how do we get equation that describe this? You are familiar with where is the Zoom this thing? You are familiar with where is it? Okay. Let me see. Where do you have a whiteboard here? Who knows? Let me see. I hope I added whiteboard to this meeting. Did I? I'm not sure. I added whiteboard to this meeting. I'm sharing my screen. Let me share. You can see the whiteboard.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, I'm coming. Let me get the mouse. The people from POT, you did physics now. You did it. You did physics at your secondary school. Is that correct? Eh?
Yes, sir. Yes, sir, we did.
Okay. And you also did mathematics. Sorry, if you just get these things. Some of these things um they are applied. So we have y equal to mx.
X
Sorry,
X
I think
plus C.
let me write it down. Y is equal to mx
MS plus C.
plus what?
C.
Plus c. You know this is the equation of a straight line.
Yes, sir.
Yes, sir.
If you've forgotten, remember it now. This is equation of a straight line where m is the what?
Intercept. The
gradient.
gradient. The gradient.
M is the gradient, c is the intercept on the y axis.
Axis.
X is the independent variable. Y is the
Variable.
dependent variable. This is fundamental physics.
Variable.
We all did. In fact, not even physics. We also did this in mathematics. But then, that's what we want to apply now. So, how do we... I will stop sharing let me share the screen at this point in time. How do we move from here how do we get this thing into equation? One of the tools you can use is MATLAB. I'm just introducing stuff to you so that you really know what to study and what to upgrade on. So eventually, by the special grace of God, when you finish your master's, you enter into academics. If you know what to do, progress, you should actually progress. You should actually progress. You can't do publications. You say you want to publish a work. You don't know how to use MATLAB. What are you going to use to model your work and plot your graphs? At that point in time, you look as if finishing these things, they are very development. You don't master them overnight, but we'll try. So we are just going to move this thing to graph now and get the model, and then we progress. How many of you have heard about MATLAB before? I know everybody in
I've heard
mechatronics
about it.
must have
Sir.
heard about MATLAB. I'm not talking about mechatronics people. How many people do we have in this meeting? We have 11 participants. Okay. So let me see if the MATLAB is still loading so that we can do this thing. While the MATLAB is loading, some of you that entered joined late, I dropped the YouTube link of the previous lesson. I said that one of the ways you can encourage me is to go there, click on that link, and like the video and subscribe to my channel for subsequent updates. That's by the way. Now we have open MATLAB. Can you see my MATLAB environment?
Yes, sir.
So I open M5. This course is not teaching you MATLAB. I'm just making mention of what you should know as a student that is doing your master's. Even if you travel abroad to do your master's, one of the basic software you must know is MATLAB. You can't run away from it. They will give you assignments that will force you to learn it. So we have here, look at this. We have here 1 to 14, right? So I say Y, or temperature is equal to 1. We're increasing by 1 up to 14. Up to 14, that is temperature. 1 up to 14. If I run this, where do I save it? No, that is not this course. What is the name of this course again? What's the name of this course again? What's the name of this course again? Okay. So this is temperature.
Robotics system. Okay.
Temperature
Sensor.
dot
Sensor.
n. So if I run it, look at what it will give you, the output. Unable to define variable temperature. Temperature. What is the problem? Oh,
That the 1:1, is it?
it's like I'm using the same name. Let me just call it temp and see what it will do. Okay. So you can see what it is. If you really want to see what I mean, you get the transpose of the temperature. When you get the transpose of the temperature, you'll be able to see the transpose of the temperature. So let's suppress this one. Can you see what it had just generated? 1, 2, 3, up to what?
14.
14. That's what we have on the Excel, which we have also generated using what do you call it? MATLAB. And then this is 0.01 up to an increment of 0.01 up to 0.14.
Yeah.
So we say again that that should be our x. X is equal to 0 at increment of 0.01 up to 0.14. We suppress it, and then if we do S complement, let's see what it gives us. That's exactly that. Sorry. That's exactly that. So we said that we plot y, or rather, we plot based on that graph, y is equal to mx. We plot MATLAB takes the horizontal value first. We plot x against, that's y against x, that's temperature
Y.
against x. This is y. This is y. Sorry. This is y. Why this one is our x. We are looking for m. So we plot this against this, and we run it. What is it saying? It's saying that error in temperature.
Sir, in line 2, the error is from line 2.
Sorry, there's supposed to be a comment here. And this is showing error. Error in line 3. Plot x against this. What is the error? They are not of the same size. We check what is the length of. Oh, we're supposed to start from 0 now. We didn't point out. Supposed to start from 0. Okay, so let's see. This is showing error.
Line 3.
Let me clear some things. Okay, this is 0, 0.01, this is 0, 1 up to 14. This is 0, 0, this is 0.01 up to 0.14. It should run now. Where list, okay. Let's see. Okay, can you see this graph?
Yes, sir.
So, well, remember we're talking, we want to move this thing, we really want to instrument this thing. So, we move from, if you want to learn MATLAB, you can contact me privately, or you want to develop capacity on embedded system. That would be a private arrangement. It's not covered in this course. We can't cover that in this course. And this is plot of temperature versus voltage. Plot of temperature versus, you can edit it, plot of temperature, just temperature versus voltage. So you insert your Y label. This is temperature, and you insert your X label. This is what now? Voltage, right?
Yes, sir.
Yes, sir.
Now you can increase the size of this thing, and can also change the color. You can also change the color, but let's give it okay, let's make it red. You can make it red. Okay. Now we want to find the equation describing this line. Hold on just a minute. So we want to, we've already corrected our data, but supposing we don't know the equation describing this line, it's not, this is just a case study. You can collect all kinds of data during your master's work. How do we fit the model? We come here, I think that should, let's look at these tools. Basic fitting. We want to get the equation of this line. We want MATLAB to give us the equation of this line. So we go to basic fitting and allow it to load. So it's opening here. Okay. From the graph, is it a linear graph?
Yes, it's a linear graph.
Okay.
Yes, sir.
I hope it's not only one person that is responding. I want to believe that others have not gone to sleep. Stanley,
We
are
are
you?
active, sir.
It's a linear graph, sir.
Yes, we know it's a linear graph. I want to confirm the availability of every other participant. Judith, Judith, are you here? Jerry, are you here?
Yes, sir, I'm here.
Okay. Nene, are you here? Nene, if you are there, you unmute yourself and talk. We have 10 people connected. Is Chibuzo there?
Yes, sir, I'm here, sir.
Yes, sir.
Um, okay, let's proceed. Something came up now. Where is it? Okay. So it's linear graph.
So I'm here. Oh, I didn't hear my name.
Okay. It's linear graph. So can you see that it has brought the equation for us?
Yes, sir.
Yes, sir.
So it has brought the equation, has just given us a model equation. So we have a model, what you call model of this. This is the model of this graph. That is the model of this data. That is the model of this data. You carried out your experiment, you get all kinds of reading. You don't know the equation that describes the data. All you just need to do is to follow the process we've just followed, plot it with the way we did it, and we fit the model. You choose the kind of after plotting it, observe the graph to know whether is it linear, is it quadratic, how is the graph tending to, how does it look like? You do educated guess, and then you can see that this number is almost zero. This number, can you see that it's zero now? I mean 4.95 times 10 raised to the power minus 16. Is it not almost zero?
Yes, sir.
It is, sir.
So what it means that we can actually remove this one so that our model will be temperature is equal to 100x. So what this thing means is that whatever value of temperature, whatever value of x we got, this is the voltage reading. Temperature is equal to 100 times voltage. That's what it actually means. What it means is that whatever value of voltage we got from microcontroller ABC, if you want to get the temperature equivalent, we multiply it with 100, and that's it. Great. So we proceed. We have already modeled our system. We've already instrumented it. Now we want to program it. Now we go back here. We go back here. We are done with this. We don't need this again. We don't need. What's happening? We don't need this again. What is happening is that is not responding. Is it because I'm sharing the screen? I want to delete this. Why is it not responding? Oh, sorry, it's running. It was running. So we delete this. We don't need this. And then we pick the controller now. We pick the controller and connect it to any of the channel. Then we want to see it. We pick what do you call it, virtual terminal to help us to see what we are doing. So we bring this here. In serial communication, you have to connect TX to RD and RD to TX. And then we now write our software. We have to write, this is embedded system. We have to write the software that will drive this. We come back to, you need to go through this lecture again and again, understand the process. We come back to what now? Our Arduino platform. So we pick a sample program just to make it simple. Basics, let's see, is there anyone that does anything to the lead analog voltage? The analog serial. Let's check this one. So we just edit this. We just edit this. We save it here. We say let's leave the name. We just edit it to suit what we want, so that we can meet up with the time. It's coming up. So this is the serial port already defined. I mean, the serial baud rate already defined. So this is A0 where we connected our this thing. We want to, when we read it, we just don't want to print it. When we read it, we said that float we said that we can define this one as float to be on the safe side. We said that float, we can call here temperature. Okay, sensor value. We can say that temperature float temperature is equal to sensor value. Meanwhile, we get to convert this sensor value to what do you call it? we're going to convert it to voltage equivalent. So we have to say, plot again, sensor value. Or we can say real sensor value. Real sensor value is equal to sensor value multiplied by 5, the highest voltage of Arduino, and then divided by the number of ADC, bit of ADC, which is 10 bits. 2 raised to power 10 is, I think it's 1024. 2 raised to power 10 is what? Why is 2 raised to power 10? If somebody is still there, you answer. 2 raised to power 10 is what? Nobody's answering again. Nobody's answering again. What is 2 raised to power 10? Everybody has gone to sleep.
It's 1024. 1024. 1024. You're correct.
Okay, we just wait for 10 seconds. I mean, a second there. So what are we doing? We read the temperature value, which is connected to A0, and then we convert it. When you read it, you will be seeing a value that is 0 to 1024. We don't want it. So we want to break it down to 0 to 5. So we multiply it with 5 and divide the whole thing with 1024, which is the analog to digital. We call it the, what do you call it? Is it the sensitivity now? The resolution. The appropriate term is the resolution. And then based on our model equation, this is what we have. Temperature is equal to 100 times voltage. And then that voltage is this. That voltage, the real voltage value now is this. Multiplied by 100. That's give us the temperature. And then we send the value to serial monitor, which is this. Look at the serial monitor. This is the serial monitor. We send it to this so that it can display on this. And then we wait for a second. That is, this is 1000 milliseconds for another reading to happen. So we compile this. We compile it. If there is no error there, we copy the hex file and put it in the controller and test it before we call it a day. So the compilation is done. There is no error. Let's look for the hex file. This is the hex file. So we pick it from there. We copy it and come here, put it here. That becomes that. So we run this. We run this and see the effect. So let's see what can you see?
4.88 printing on the serial monitor.
4.88. So, of course, there is an error of 0.02, right?
Yes, sir.
There's an error of 0.02. Well, that's what we begin to talk about instrument accuracy. Let's see if it is consistent. You have to use software to correct it. This is 6. 6 is reading this. Let's check the software. Probably I suppose to use. Let me use 1023 here and see exactly what that is the challenge. Because 0 to 1023 is 1024. Let's see whether it will correct itself. Okay, we'll come back, we'll stop the simulation and start again. Let's see what it gives us. Okay, still doing the same thing, which means there is okay, 8, 9. At least we can see that the integer value is correct.
Yes, sir.
That's 10. We go back to 0. What does 0 give us? Okay. So let's see what 27 gives us. Okay, which means if we declare this thing at this point is it just you use your initiative. If we declare this as an integer and declare this as an integer, does it change anything? Declare this as an integer. You check, does it change anything? Ah, I'm not getting expected result. What did I do? What did I do? Integer, temperature integer. It's like there's a problem there. So we revert to what was there. There's a problem in the division when you change everything to integer. Okay. Try again. So that's it. We have been able to instrument this sensor, and then it has an error of 0.33. So that's that. This is time for questions. This is time for questions and the answers. I'm waiting for your question and answers, or have we succeeded in confusing you more? Just say your mind.
We are
Nobody's
good, sir.
talking.
We are good, sir.
Hello,
Okay.
sir, please, I want to ask a question based on that error message we're having.
Can you
For
speak
instance,
up?
now you're inside the exam
Speak
hall
up.
and
I'm
you
not
are
hearing you very well.
okay, sir. Sir, you hear me now?
Go ahead. Let me try to
Hello.
hear you.
Okay, I say for instance now maybe you are inside the exam hall and you are solving, you are having this error message, and you try with, let me use for the two approach you use without getting the answer. Will you just write what your calculator is showing?
You try the two approach without getting the answer. Which approach? Is it the programming?
Yes, sir.
How do I ask your question again? Can you repeat your question? Judith, ask your question again.
I say, sir, when you are doing the programming, the
Yeah.
first one you use, you said you changed the 2 raised to power 10. That's the one we got 1024. You make it to 1023. And you're still having error message. I was not asking, in a situation, someone you change and you are still having error with the programming. You still write this error as your result. Will it be okay? That's my question.
Okay, it will be okay now, provided you didn't move away from 1023 and 1024, because 2 raised to power 10 is 1024. But you know that we know that in digital counting, the counting begins from 0, not from 1. I was actually changing it to see whether is it because we started counting from 1. If we start counting from 1, it becomes 1024. If we start counting from 0, it becomes 1023. In any case, if you are building an instrument and as a programmer, what you actually need to do is to find a way to fine-tune your software to make the instrument sensitivity to be as accurate as possible. If it means subtracting, if you notice that 0.33 is constant, you can actually go back to the model and remove 0.33 for every reading, so that the value will be exactly the value you expect. Look at what I mean. I mean this. Our result is showing 0.33. So I come back here and minus, put this in brackets, minus 0.33 here, and run it again, since that is the problem. It's coming to the peak of the time. Okay, so let's check the results. If it doesn't conform, we just leave it. We've almost exhausted our time. Can you see what Judith, can you see the effect now? Is Judith still there?
Yes, I'm seeing it.
In a nutshell, what I said is do everything you can as use your intelligence and fine-tune your software to get the accurate results. Does it answer your question?
Yes, sir. Thank you, sir.
Eh?
Yes, sir. Yes, sir.
Okay, just use your initiative. Of course, that's that. Use your initiative. You have gotten an approximate value of your result by instrumentation. Fine-tune your instrumentation so that you get the appropriate result. What will be instrumentation that you will have a reference instrument. For example, if you are trying to build a temperature device, you should use a reference instrument, another thermometer, as a reference point to be sure the one you are building conforms to the temperature. If your reference instrument is reading 29 and you are getting 29.05, you fine-tune your software to get the exact value so that your instrument will be accurate. Okay, that's that. Is there any other concern? Is there any other concern?
No, sir.
Okay, so you do me a favor now. Every one of you, if you have not done so, go to this link. You go to this link. Let me share my screen again. So you go to this link now. Go to this link, click on this. And that is the video of the last lecture. Like the video there. Like the video there, and you can subscribe to my channel so that my profile will continue to increase. That's one of the way. What I'm doing now is one of the productive works. One of the productive work. That is one of the ways to grow in academics. So please, let's do that within the next 3 minutes, if you have not done so.
All right, sir. All right.
Don't postpone it, just do it right away. Copy that link and be placed on your search engine, on your browser.
Sorry, sir. What slide is the link?
You say?
What's the number of the slide? What's the number of the slide that has the link?
A slide. Copy the YouTube link. Look at it. Can you see my screen? Can you see my screen?
Yes, sir.
Copy it from the chat and paste it on your browser, and then you get there and subscribe to my channel and like the video. I don't know whether that answers your question.
My chat is empty. There's nothing here, sir.
You say? It's like you're having the 12 challenge. Please, next person so that we can start. We don't really have to. You can ask your question. Let me hear what you're saying.
My name is Loy Rebecca Onyechi from the Department of Process and Robotics.
Department of, okay. Go ahead. Okay. Oh, okay. That's okay. In order not to, I'm responding to the video. Just to the chat, because we get to take attendance. Go to the chat, your name, your department. Okay. How many people do we have here? We have 8 people. It's all right. So the department, your registration number. In absence of any other concern, one of you should what's time? That's that. Give vote of thanks. I think POT people did that the other time. Let's have somebody from Mechatronics this time around. Give us a vote of thanks so that we can close. Cost rep, Mechatronics, Stanley, if I see them.
Good evening, sir.
Good evening.
This is Gatson Ozojimekpelime from Department of Mechatronics.
Okay, go ahead.
Yes. We want to thank you for your effort. It's not easy being up for students at this hour of the day. And we want to apologize for missing yesterday's class. It wasn't intentional. We didn't plan it. It was just misinformation that caused it. We were actually waiting, hoping a link will be sent to us. Unknowingly to us, Stanley informed us that we were supposed to use this same link that was sent previously. That was how we missed out on yesterday's presentation. So we want to apologize. We are sorry, and it wasn't intentional. And thank you very much for your understanding and your continued effort to our well-being and our improvement. We deeply appreciate your effort. Thank you very much, sir.
Okay.
Thank you.
Okay. It's all right. So you prepare for your presentation. That's mind me. The people from POT, are you listening? Are you listening? Can you hear me?
Yes, sir, we can hear you, sir. We can hear
All
you.
those presentations you did, you need to share it among yourself and then study it. Your questions will come from there. You need to know what other persons have presented. When the mechatronics people present their own, they do the same among themselves. When people in biomedical engineering did do their own, they will do the same. If you fail to do your own, you will score 0 in continuous assessment, and then you stand the risk of answering questions from other departments. That's just the thing. Okay. Thank you very much. We shall call it a day today. Has been 2 hours of serious engagement. When are we meeting again? It should be the same time. Today is 21 plus 7 is 28. So we are meeting on 27 and the 28 to finalize things. On 27, all the people that didn't do presentations this week should do their presentation. And then by 28, we try to summarize the lectures and look at how the exam or the exams will look like. That's that. God bless you. We'll call it a day here, please.
Thank you very much, sir.
Okay.
Thank you very much, sir. We're grateful, sir. Good night, everyone.